When people think they understand wood, that's usually when problems start. Solid wood looks simple. It's familiar. It feels intuitive. But in real buildings, solid wood is one of the most misunderstood structural materials in construction. Not because it's unpredictable, but because most people never learn how it actually behaves once it's installed. You'll learn what solid wood truly is, and why that single definition controls almost everything about its strength and movement. We'll clear up the biggest myths around softwood and hardwood, and explain why nearly all modern structural framing relies on softwood, not because it's weaker, but because it behaves better in real buildings. In next video, we'll go deep into lumber sizing, including why a 2x4 is not what you think it is, how nominal sizes mislead beginners, and how professionals choose depth, width, and length to avoid long-term problems that don't show up on inspection day. Let's start at the foundation, with what solid wood really is. When construction professionals talk about solid wood, they are not making a value judgment. They're not saying it's better, worse, traditional, or superior. They are describing a manufacturing condition, and that distinction matters more than most people realize. Solid wood means the structural member was cut directly from a log and shaped by sawing or planing. It has not been layered, glued, pressed, strand-oriented, or chemically reassembled. What you see is one continuous piece of material that once grew as part of a tree. That single fact controls almost everything about how the material behaves in a building. Because solid wood comes from a single piece of timber, it behaves differently in different directions. Engineers describe this as anisotropic behavior. In practical terms, solid wood is strongest parallel to the grain, weaker perpendicular to the grain, and far more sensitive to restraint and moisture than most people expect. It does not expand and contract evenly. It moves differently depending on orientation, exposure, and how it is fastened into an assembly. This is fundamentally different from materials like steel, which behaves the same in all directions, or concrete, which becomes dimensionally stable once it has cured. Solid wood never fully stops responding to its environment. Long after installation, it continues to absorb moisture from humid air, release moisture into dry air, and change dimension as conditions shift. That doesn't make solid wood unreliable. It makes it honest. Professionals don't use solid wood because it's perfect. They use it because its behavior is known, repeatable, and manageable when it's selected, sized, and installed correctly. The problems begin when people treat solid wood like a static material, expecting it to behave like steel or concrete when it simply doesn't. Understanding that solid wood is a living, responsive material is not a poetic idea. It's a practical one. Once you accept that movement is inevitable, solid wood stops being unpredictable and starts behaving exactly the way professionals expect it to. With that foundation in place, the next question becomes obvious. If solid wood moves and responds to its environment, why does it still dominate light frame construction? That's what we'll break down next. Solid wood dominates light frame construction not because it is flawless, but because it solves more problems than it creates when used correctly. Relative to its load carrying capacity, solid wood is lightweight. That matters. It reduces foundation demands, simplifies handling on site, and allows structures to be assembled quickly without heavy equipment. Crews can lift it, cut it, adjust it, and fasten it with simple tools, even under imperfect field conditions. Solid wood is also forgiving during construction. It tolerates minor misalignments, field modifications, and sequencing challenges better than many alternative materials. When conditions aren't ideal, which is almost always, solid wood absorbs error instead of magnifying it. Another reason solid wood performs well in light frame buildings is how easily it integrates with fasteners and connectors. Nails, screws, bolts, and metal hardware interact predictably with wood fibers. Connections can be reinforced, modified, or repaired without redesigning entire assemblies. Just as important, solid wood tolerates the realities of job site moisture better than many alternatives. While moisture affects its dimensions, It does not immediately destroy its structural capacity. The way corrosion can affect steel or improper curing can compromise concrete. When detailed properly, solid wood weathers construction phases remarkably well. But there's an important condition attached to all of this. Solid wood only works when builders understand what it will do, not what they wish it would do. It expands and contracts. It dries. It moves. And if those realities are ignored, the same advantages that make wood attractive can turn into long-term performance problems. Professionals don't rely on solid wood because it's cheap or traditional. They rely on it because its behavior is predictable within known limits. When those limits are respected, solid wood delivers durable, resilient structures at a scale and speed few materials can match. The moment someone assumes solid wood will behave like a static material, problems begin. That leads directly to one of the most common misunderstandings in construction: the confusion between softwood and hardwood. The terms softwood and hardwood do not describe how hard the wood feels when you touch it. They don't describe strength, durability, or quality. They describe the type of tree the wood came from, and nothing more. Softwoods come from evergreen trees. Hardwoods come from deciduous trees. That's the entire definition. Everything else people assume from those names is usually incorrect. Here's the part most people miss. Almost all structural framing in modern construction uses softwood, not hardwood. That decision has nothing to do with softness or weakness. It has everything to do with how the material behaves when grown, milled, and installed at scale. Softwood trees grow faster, straighter, and more consistently. That makes their lumber available in long, uniform lengths with predictable grain patterns. Softwood machines cleanly, performs reliably under structural load, and behaves consistently across thousands of pieces, which is exactly what large-scale construction requires. Hardwoods are not inferior. They are simply used differently. Hardwood trees grow slower and with more variation. Their lumber is often shorter, heavier, and less consistent in long structural lengths. That makes hardwoods less practical for framing entire buildings, even though many hardwood species are technically stronger. Professionals use hardwoods where their characteristics matter most. You'll see them in stairs, flooring, doors, trim, and other areas where appearance, wear resistance, and surface durability are more important than long-span structural behavior. This is why experienced builders never ask which wood is better. They ask which wood is appropriate for the job in front of them. Strength alone does not make a material suitable. Predictability, availability, and long-term behavior matter far more. If this explanation helped you see wood differently, support the channel by liking this video and subscribing. It helps these professional-level explanations reach more people who want to build the right way. See you in the next video.